Hi, my name is Lang Hames, and this is going to be a deep dive into the ORCv2 APIs. This talk is going to follow on from the Updating ORC for Concurrency talk that was given in the developers meeting in 2018. You don't have to have seen that talk to appreciate this talk, and I'll give a brief overview of ORC before we dive into the details today. Content from that talk remains relevant, so if you are interested in today's talk and you're looking for more information, that's a good talk to check out. Compared to that talk, there's going to be fewer API examples today and more concepts. But you'll be able to find example code for many of the things that we'll talk about today in the LLVM examples, ORCv2 examples directory. And my hope is that the concepts and design ideas here help you place those API use cases and examples into context in the design of ORC. So first up, what is ORC? It's short for on-request compilation, and it's often referred to as LLVM's JIT APIs, and certainly people do build JITs on top of this. But ORC itself is not a JIT. It's a library for building runtime linking environments. And by that, I mean systems that patch relocatable object files into running processes. In ORC, you can describe programs and libraries as collections of program representations. And unlike regular builds, you don't have to have compiled those program representations up front. So you can add objects and archives to an ORC program, but you can also add uncompiled LLVMIR or even custom program representations like ASTs. Whatever program representation you're adding, you always initially wrap that representation in a materializer. And a materializer is just something that ORC can call to generate the definitions of the contained program representations on request. So the animating force in the ORC APIs is symbol lookup. ORC will run the materializers that you've registered to define symbol addresses in response to symbol lookups. So if you've added a materializer for a symbol foo, it's the first lookup for the symbol foo that will cause that materializer to run. Since this is a really central idea, we'll take a moment to look at it in more detail. Materialization is a really generic concept. It just means assigning meaningful addresses to sets of symbols. So this can involve compilation, but it can be much simpler than compilation, simpler even than linking. I'll give some examples in a moment, but however it's done, materialization always involves 3 steps. First, you're going to resolve the symbols that you're materializing to some assigned addresses. The symbol definitions don't need to be there yet. You're just going to create the association, symbol goes to address. Next up, you register the dependencies of the symbols that you're defining on any other symbols that they use. So if you were materializing a function foo and it calls another function bar, you'd register the dependence symbol foo depends on symbol bar. Finally, you tell ORC once you've written the definitions of the symbols out to the addresses that you assigned in step 1, and you're done. You've materialized the symbols. ORC uses the dependence information that you give it in step 2 to make this whole system concurrency safe. So you can run materializers concurrently on multiple threads, even if they contain program representations that refer to one another. And you can issue symbol lookups on any thread at any time and be guaranteed that you won't get a result back until that result is safe to use. I mentioned that these materializers can be very simple. The simplest materializer is the absolute symbols utility. This is provided in tree for you, and this just creates an association between a symbol name and an address. This is a way that you could, for instance, name a hardware buffer for the sake of your JIT code. The steps to materialization for this materializer are just that we resolve each of the given symbols to the given fixed address, we register no dependencies, and we tell ORC that the symbols have been omitted because there's nothing for us to do. So that's the simplest materializer that you can come up with. An only slightly more complicated one, but a much more interesting one, is the lazy reexports materializer. This is how we enable lazy compilation in ORC. Lazy reexports takes a map of stub function names to function body names. And it's going to create the stubs for you and arrange that if you call the stub at runtime, it's going to trigger compilation and then jump to the stub, the function body. So the way it does this is it reserves memory for the stubs and resolves each of the stub symbols to one of the reserved addresses. It registers a dependence of each stub on the ORC reentry function, and only the ORC reentry function. The stubs don't depend on the function bodies at materialization time. And then it splats out some stub bytes to memory and applies protections. So that's how we generate stubs for you in ORC. There's no compilation involved. There's not even any linking involved. We just reserve some memory, write out some stub bytes, and that's about it. Now, if you call one of those stubs at runtime, We're going to call into that reentry function, which does a register state save, looks up the function body in the JIT, which triggers materialization, restore the register state, and then jump to the function body, and we'll update the function stub pointer so that future calls go to the body. We take care of all of that for you. All you have to do is give us the map of the stub names that you want to the function bodies that you want compiled. So materializers can be really simple, but the selling point of ORC is that it makes it easy to build complex materializers. And what we really want to be able to do is to use existing compilers to build materializers. The component that ORC gives you to help this process along is the ORC Runtime linker, which can materialize symbols from relocatable object files. So if you have a relocatable object file that defines the symbols that you want to materialize, you just run that object file through the runtime linker to materialize those symbols. We'll look at this in more detail later, but the 3 steps required here. First, we reserve memory for the symbols defined by the object file. Then we register the dependencies that are embedded in the relocations of the object file. And finally, we apply those relocations, write the relocated memory to the executing process, and then tell ORC that we're done. So if you have an object file that defines the symbols that you want, a materializer for those symbols is the closure that runs runtime link on that object file. And this generalizes really nicely. If you have some program representation P and a compiler for P that produces relocatable object files, then a materializer for the program representation P is just the closure that runs this expression. Compile P and then send the output to the runtime linker. So that's a sort of whirlwind overview of ORC. You can compile concurrently, you can compile lazily, and you can build materializers out of regular compilers, but have those compilers run on demand for you at runtime. So that brings us to what's new in ORC and the reason for today's talk. It's been a few years since I've given an update, so there are a lot of new features. We now have debugging support for JIT'd code on both Darwin and Linux. The Linux support has been around for, I think, a few months now. The Darwin support is brand new as of this weekend. We have native code and relocation model support. It used to be in MC-JIT and earlier versions of our JIT APIs that if you wanted to generate code for the JIT, you had to do it with special mode flags, for example, the large code model. On some platforms where we've got support, that's no longer true, and you can actually just give it totally regular compiled object files with the small code model and position-independent code. Similarly, we now have support for native thread local storage on Darwin, and we have partial support on Linux. So on x86 Linux, we support the ELF General Dynamic TLS model, but not the other TLS models yet. We also have language runtime support on Darwin, so we can now load Objective-C and Swift code into the JIT. This requires special support because those languages embed metadata for their respective runtimes into the object file, and that's loaded by the system loader. We can now emulate that process, and that's how we're able to load up objects for Swift and Objective-C under the JIT. There's a theme to these last 3 points, which is that MC-JIT made it easy to reuse existing compilers to build a JIT. We're moving instead to a slightly different model where what we're trying to do is emulate the object runtime. If we can emulate the features of the object runtime, that is the environment that we usually link code into, then not only can we reuse existing compilers, we can reuse existing pre-compiled code. That includes existing static archives that you might have around. A particularly interesting use case for this is we'd love to just be able to link compiler RT into your JIT so that you can use compiler RT features without having to build a second copy of our compiler RT specifically for the JIT. So that's what we're working towards. A few other features in the list. We've got JIT'd code removal. This was a feature in ORCv1 that we lost when we moved to ORCv2. That's been restored. So you can add code to the JIT, but you can now take it out again as well. We have simplified and improved remote execution support. ORC can run the code that you're generating in the JIT in the current process, but it can also run it in a separate process, and you might want that for stability or security reasons. We've made that easier, and we've made sure that the features that ORC provides work uniformly, both in process and across process. We have new C APIs for a lot of this, not all of it yet, but a lot of this you can try out from the C APIs. And then a theme of this talk is we're building towards a new run JIT'd program function. We've always given you the ability to run functions in JIT'd code, Now we want to give you the ability to say, I want to run the whole program, the initializers, the main function, and the static destructors. And we now have a way to do that. There are several new components involved in making all this work. The biggest is JITLink, which is a new runtime linker to replace runtime DYLD. That's what we'll spend most of this talk on. We also have a new runtime library, the ORC Runtime, which provides the executing process side support for some of these features. Finally, we have a new API called Executor Process Control that abstracts away that executor process boundary so that if you talk to this API, you can toggle whether you're JITting code into the current process or a separate process just by changing which implementation of executor process control you use. So we'll dive into JITLink. I guess the first question is, if we already had a runtime linker, why are we abandoning it? And the answer is that it had a gray box design that hid too many details to implement some of those advanced features like thread local variables or Swift or Objective-C support. As an example, it wouldn't give you accurate section sizes for the sections in your object files, and this made it difficult to parse the metadata that you need to register for certain features. It also had a fixed linker algorithm that was shared between all formats and architectures. This was not customizable, so it baked in various trade-offs that we would have liked to have been able to choose on a case-by-case basis, and it was brittle. Fixes for one format or architecture could easily affect another. That also made it difficult to fix. It would have been a very destabilizing process to try and turn runtime DYLD from what it is now into what we might want it to be. So instead, I started from scratch with JITLink. I'm very happy with how that's gone. JITLink first landed in 2019, and we've been adding new architecture and format support since then. Unlike runtime DYLD, the new runtime linker exposes its core data structure, which is called the LinkGraph. And you can install parsers into the linker pipeline to inspect or modify those link graphs. This solves the problems with opacity and control that we had in runtime DYLD. You can now see every object being linked under your JIT in exactly as much detail as the linker sees it. And you can modify the link graph to get the kinds of linker behavior that you want. This is a big deal. This is the first time that we've had control in the LLVM JIT APIs over the code being JITted right down to the instruction level. So you can lay out individual bits of your code. You can see and modify every instruction as it's passing through the JIT. As you'll see, we can implement some really cool things on top of this. JITLink has a nice clean design. We have carefully separated architecture and format support, as I'll show in a minute. We have error checking from the ground up. So we check your object files as we're parsing them, and we range check your relocations as we're applying them. In the spirit of LLVM, we have a command line tool that's a thin wrapper around this library that lets you run relocatable object files directly from the command line without linking them first. Finally, we have reasonably good testing for this. We have lit regression testing with JITLink check, which is just the old runtime DYLD check infrastructure rebadged, but we have better test coverage for the supported architectures in JITLink. We also have unit tests for the link graph and all of the associated APIs. Unfortunately, we don't have support for all architectures yet. So on Marco, x86, and ARM64, we have near complete support. On ELF, we mostly support x86-64. We're missing some of the relocations for large code model and static code models, but otherwise it's well supported. We have a partial implementation of RISC-V and a very new implementation of ARM64. And all of these were community contributions. So thank you so much to all of the people who've been contributing code to these APIs over the last couple of years. We're always looking for more volunteers as well. So if anybody's interested in getting involved, writing new JITLink backends is a really nice sort of medium-sized, low-level project within LLVM. If you're interested in getting involved in that, please reach out to me and let me know, and I'll be happy to help you get started. Similarly, we don't have COF support yet, so we don't have native support for any of this on Windows. Implementing COF support would be a slightly larger project because you have to deal with the object format details as well as the architectures, but it's still doable and self-contained. So if you're interested and you're a Windows user, reach out to me. I'd be happy to help you get started with that as well. A good source of documentation for this is the LLVM docs jitlink.rst document, in particular the tips for JITLink backend developers section. I thought, for the sake of anybody who might be interested, and also just because it's neat to look under the hood, we would take a look at the JITLink pipeline. You don't need to understand any of this to use JITLink, but it's cool to see how it works. So we start off with an object file. We run that through a link graph builder. and the output of that is a link graph for our linker. Now, the link graph builder that's parsing the object file, the bulk of the parsing work is in dealing with the format details, and these are independent of the architecture being linked. So we lift most of the format parsing code up into a link graph builder base class. For instance, we have a generic ELF link graph builder that knows how to build sections and symbols and most of the other parts of the graph. So if you're writing a new backend, the only thing you need to do is add the architecture-specific parsing code, which is usually just the relocations. So these things are pretty easy to write. Now, once you do have your link graph, you run that through your JITLink linker. Even more so than the link graph builder, this is just a mix-in of two things, a generic JITLink pipeline and the architecture-specific relocation support. And we're linking a single object file here, so we have to link it into something, and that something is a linking context. The linking context provides the memory management that we'll use to get JITted code into the executing process. It handles parse pipeline modification to install user-supplied parsers. So we've structured our linker as a pipeline. The linking context is going to be able to modify that pipeline to insert your parsers. The linking context handles key event notifications. So the pipeline tells the context when we assign addresses to the symbols that we're defining. It tells it about the dependencies between the symbols, and it tells it when we've emitted the symbols into the remote process. And if you remember that slide about materializers from back at the start of the talk, these are just the 3 steps of materialization. So this whole thing is just an elaborate ORC materializer. So the linking context connects through to the ORC execution session and publishes those events, and that's how we materialize the definitions in your object file. The linking context also provides external symbol resolution. So when we need to look up external symbols, we issue a lookup to the linking context, which forwards it through to the execution session. This is how a sort of swarm of linkers, each working on an individual .o file, can nonetheless cooperate to link those .o files together. Each individual linker is publishing the addresses that it assigns and then looking up addresses published by the others in order to complete the relocation work. If anything goes wrong here, we report an error through the linking context to the session and we tear down all the symbols. But if everything works, the output of this process is fully linked memory in the target process. So that's the pipeline. Now let's take a look at that link graph data structure that's at the center of it. We'll construct a link graph for this simple C program on the left here. Let's assume we've compiled it with clang-c-o on Darwin. So the output of that will be a Marco object file. First up, we've got that static variable x. In the link graph, that's going to become a symbol node. Every named global value in your C program is going to get one of these symbol nodes in the link graph. And it's _x because this is a Marco object file. And that's how Marco lowers C symbol names into assembly level symbol names. And this graph is an assembly level representation. Now, x is defined in this graph. So we also have a block node, which gives you the initial memory content for the symbol x. In this case, it's just the 32-bit value 7. And this is a variable, so it lives in the Marco data section. So these are the 3 nodes in a link graph: symbol nodes, block nodes, and section nodes. Next up, we've got an external variable y, so we introduce a symbol node for it, but it's not defined in this graph, so there's no block node and there's no section. We've got the getX function, so we have a getX symbol node. We have a block for that, which contains the unrelocated machine code for the function getX. This is x86 machine code, so we can see that instruction string. This is a function, so it's part of the text section. And there's a symbolic reference from that getX function to the x variable. That's going to become a relocation in the object file to fix up these set of zeros here, which are one of the instruction operands. Relocations are represented by edges in this graph. In this case, we have a delta 32 edge pointing from the bytes to be fixed up to the symbol they reference. Delta 32 means that the expression that we're calculating is the 32-bit delta from the address being fixed up to the target address. So that's the final element of a link graph, edges. A link graph is symbols, blocks, sections, and edges. Finally, we've got our malxy function. This has, again, unrelocated machine code bytes as its operand. It's part of the text section. And this time we've got 2 locations that need fixing up. One is for the call to getX. We represent that with a branch 32 instruction. So we distinguish branch references from delta 32, which are data references. So we can see every call site in your JIT'd code, symbolically where it's calling to. And once we've assigned addresses to the nodes in this graph, we can see the address that the call lives at and the address of the thing that we're calling to. And then the global offset table load. Y could be anywhere in the 64-bit address space, so we can't reference it with 32 bits of displacement directly. So the compiler will have inserted a global offset table load. So we need to lower this edge, which JITLink knows how to do, into a global offset table entry. We have a delta 32 edge to that, and then a pointer 64 edge to fix up the global offset table. So this is what a link graph looks like. The graph's already a bit dense, so I haven't shown it on this graph, this particular graphic, but these nodes have extra properties. So symbols have names, but they also have linkages and scopes. Blocks have alignment constraints, and sections have memory protections. And you can mutate all these properties. So you can go and point edges at different targets. You can change the instruction stream in the blocks. You can change the memory protections on sections. The way you make those mutations is with passes. So a pass is just any function object that you can call on a link graph that returns an error. And since we're generating pass pipelines on demand, what you usually write is an object linking layer plugin. You write your plugin, and for each new link, the object linking layer plugin instances are given a chance to modify that pass pipeline. The pipeline has 5 stages, so the plugins can install passes at any of those phases. There's a pre-prune phase where you can mark elements live to prevent them from being dead stripped out of the graph. A post-prune phase where we can still add or remove content before we allocate memory. So for instance, this is where we insert global offset table and procedure linkage table entries. There's a post-allocation phase where you can respond to the addresses assigned to the symbols defined in this graph. This is mostly useful for internal bookkeeping. There's a pre-fix-up phase where we can react to the final addresses of everything in the graph. So at this point, the external symbols have been resolved. At this point, we can do things like instruction stream optimization, and we have built-in optimizations to bypass global offset table loads and procedure linkage table loads if the targets of those loads are within range, or if the targets of the calls are within range. Finally, there's a post-fix-up phase where you can react to linked content after fix-ups have been applied. And again, this is useful for bookkeeping and setting up metadata registrations. So I thought we'd take a look at what a pass looks like. Let's enable runtime redirection by inserting stubs and redirecting calls in a graph. So we're going to add the ability to change where function calls go at runtime. The pass to do that would look like this. Interpose functions is, for all blocks in the graph, for all edges in the block, if the kind of edge is a branch 32, then we're going to change the edge target to point at a stub for the original target rather than the original target itself. And then we return error success, and we're done. This is really cool. This is slightly simplified from the real version, but only very slightly. And with a few lines of code, we've injected the ability to redirect calls at runtime, which didn't exist in the original objects. Because this is a pass and it runs at the linker level, it applies to all code that we load under the JIT, regardless of the input language or whether this was a precompiled archive. The other thing that's really neat about this is that this isn't the only way that we could have enabled runtime redirection. We could have waited until after all of the addresses were assigned and then recorded the call site locations and rewrote text memory directly to redirect the calls. Now, you can only do this if you can get the ability to write executable memory, which some systems don't allow for security reasons. But the important thing to note is that we don't force any particular trade-off on you there. You can choose whichever one fits your security and performance constraints. There are a ton of things that we can do with passes. We can have different global offset table and procedure linkage table lowering schemes. We can do instruction stream optimization. We can redirect calls and branches, insert instrumentation. And this is rich enough that we can replace the old JIT event listener APIs. Anything that you could have done with a JIT event listener, you can instead do by installing passes. So moving on from passes and LinkGraph, the other big API in JITLink is the JITLinkMemory Manager. This is responsible for getting JITted code into the executor, so it's quite common for JIT clients to be able to want to write their own memory manager. If you're going to write your own, there are 3 operations to implement. The first is the allocate operation, this has to allocate two kinds of memory: working memory for JITLink and target memory in the executing process. So the working memory is what holds the block content while the linker is working on it. This is where we apply fix-ups. The target memory is the memory that resides in the executing process. There's a finalize operation, which is responsible for transferring the content from working memory to the executor memory. This then frees the working memory, applies memory protections, and then it runs finalization actions, which I'll talk about in a moment. Next up, the deallocate operation has to run deallocate actions, and then it releases executor memory. So those are the three things you need to write if you want to have a custom memory manager. All those operations are asynchronous, and allocate has control over the layout of the graphs right down to the block level. So we pass the graph itself into the allocate operation, and the allocate operation is responsible for assigning working and executor memory to all blocks in the graph. If you don't want to control things at that level of granularity, there's a basic layout class that you can construct from the graph that'll give you a segment-based view of the world. So it'll just tell you, you need so much read-writable memory, you need so much read-executable memory. You satisfy those requests, and then you let basic layout take care of the assignments to the individual blocks. Finally, those allocation actions that I mentioned, these are triples of function pointers and buffer ranges as an address and a size. And we call the function on the given buffer range. These are attached during finalization in the memory manager as pairs of finalize and deallocate actions. The finalize actions run after we've set permissions on JIT'd memory, but before the finalization process returns. And the deallocate actions run during deallocation before the memory is freed. So this can be used to attach section registration and other operations to memory allocation calls. So for instance, registering EH frames can be done by attaching allocation actions. There are two benefits to this. The first is that we've got reduced IPC RPC. We can piggyback on top of the memory allocation call to do these registrations. If you can register all of your sections through these allocation actions, which is the usual case, then you can link an object into the executing process with just one IPC round trip. And then the other benefit of this is deallocation actions can run even if the JIT is disconnected. So if you're running in a remote setup and something drops out, we can, rather than having to tear down the executor process, we can deregister all of the JIT'd memory and free it and leave you hopefully in a clean state, rather than having dangling pointers from, say, libunwind into JIT'd memory. Leaving JITLink for a moment, we'll go over to the ORC runtime. So JITLink gives us the visibility into the linking process that we were looking for, but we need executor-side support to act on the newly available information. The ORC runtime provides a home for that executor-side support code. It contains JIT versions of the dlfcn.h functions. These are dlopen, dlsim, dlclose. If you're not familiar with these, they let you load dynamic libraries and look for the address of symbols in dynamic libraries. And they're useful because they give a reasonably well understood way of thinking about how we run initializers in our program. We also have at-exit interposers. So if you ever used, say, C++ static destructors with MCJIT, you might have had the unpleasant experience of your code crashing at process exit time. And that was because we register JIT'd static destructors with the process at-exit, and we try to run those destructors long after the JIT had been torn down. By providing at-exit interposers in the runtime, we can avoid that problem and run your JIT'd destructors before we tear the JIT down. We have a JIT-friendly thread local variable implementation that can handle adding new code to the library at runtime. And finally, we're going to move the JIT reentry functions there. Those JIT reentry functions that do the register state save and state restore currently live in LLVM, and we have a kind of awkward injection process to get them into the executing process. Now we can just express those in the ORC runtime. Separate from the runtime, but intimately connected to it, is the ORC platform. This is an object on the controller side of this connection, along with the JIT and the rest of the LLVM APIs. So this attaches to an execution session, and it coordinates with the ORC runtime to emulate object runtime environments. For example, we have a Marco platform implementation. And if you attach that to your JIT and add Marco objects to your JIT, we expect those objects to behave in the JIT'd program exactly as they would have behaved in an ahead-of-time program, including registering language metadata, running initializers, and everything else. The way this works is that the platform object is notified when new JIT dilibs are created. And I haven't mentioned JIT dilibs until now, but JIT dilibs are just the containers that we put materializers into in ORC. So the platform is notified when these containers are created, and it's notified when new materializers are added to the system. And it can identify materializers that contain initializers. These have a special symbol attached to them. So the platform can install plugins which use JITLink parsers to identify key sections in the object files during links, like exception handling frames, thread local variable data, static initializers, language metadata. And it can communicate those section addresses to the ORC runtime. It's good to do this within the platform object itself, because now we don't have to come up with generic abstractions about language metadata or initializer sections that fit all of the different object formats. Instead, we push all of those object format specifics into the platform class, and the rest of ORC stays blissfully unaware of these details. The last API that we need to tie all of this together is executor process control. This is that abstraction that lets you forget about whether you're executing code in a remote process. So this can report the executor process triple and page size so that you can configure your JIT correctly. It provides a suitable JITLinkMemory Manager for the executor process. And it supports function calls in both directions for functions with this signature. And this is basically a function that takes an array of bytes and returns an array of bytes. Now we provide convenience wrappers on the executor process control base class for serializing and deserializing various value types into the argument buffers that are given to and returned from wrapper functions. So when you call these things, you often don't need to deal with the serialization yourself. You can just use the convenience wrappers that we provide. So we'll see what this looks like when you tie it all together, how we can emulate DL open in the JIT, even though the code we're DL opening hasn't been compiled yet. So over on the left here, let's imagine that we have some controller process. It has an ORC JIT in it. There's a platform attached to an execution session, and that execution session has a JIT dilib with a few materializers in it. And then separately, we have an executor process. This process has been running for a little while. We've linked the ORC runtime into it already, and it has that ORC runtime DL open emulation. We're going to arrange to have that DL open called somehow, and we'll see how that communicates with ORC. So when we do the DL open on the JIT'd code, ORCRT DL open is going to call get initializers on the platform, and it calls via that executor process control API. Get initializers, as I said, is able to track which materializers have initializers in them. So it just issues a lookup for those initializer symbols. The symbol lookup triggers materialization because that's the contract in ORC. So we're going to materialize any modules with initializers. Let's assume in this case, it's module 2 and 3. So we'll run the pipeline and we'll get to JITLink. The platform has installed a plugin so it can see all of the sections being linked into the process. So as we're injecting the code containing the initializers, we can also record all of the initializer address ranges and save them off into an ORC platform state object. Now, by the time that lookup that was issued by the platform returns, we're guaranteed to have aggregated all of those initializer address ranges into the platform state object. So the platform's lookup returns, then get initializers can return, and now ORCRT DL open has all of the information that it needs in order to do the DL open sitting there in the platform state object. It can walk over that, register the language metadata sections with the language runtimes, run the static initializers and everything else. So the nice thing here is the format details are contained to JITLink, the platform, and the ORC runtime. They don't pollute the rest of the ORC APIs. I mentioned we're building towards a run JIT'd program primitive. So now we can write it. ORC runs functions, not programs, as I mentioned, but we can now define a function that runs a program. And this is the function, and you may have played with something like this yourself if you've ever used the DL open APIs. Running a program is just going to be a JIT'd DL open of the dilib containing the main function, and then we DL sim the main function to get its address, call it on the given arguments, and then DL close the main function. So I'll jump over into my terminal window and show you what that looks like. 1 second. Hopefully everybody can see this okay. I've got a little sort of Rube Goldberg program here that we're going to use to test this idea out. It contains some Swift code with a class and a virtual method in it. And then it calls into some C++ code that uses static initializers, thread local variables, and exceptions. And all of these things have to work if we're going to get the correct answer out of it. So I mentioned we had that command line utility that can run object files in place. We're going to run LLVM JITLink. We're going to tell it to DL open the real Swift runtime dilib, load up the ORC runtime, and then run that on the 2 object files containing our Swift and C code. And if we do, you can see that that correctly produces the result here. I also mentioned that we can run this stuff out of process with only a few lines of code. So LLVM has the LLVM JITLink tool. It also has a remote executor tool. I'm going to load that up and tell it to listen on a TCP port, and then jump back over to my JITLink invocation here. And I'm going to tell it to run this in remote mode. So I'm going to send that same program over to the remote executor, and you can see it behaves the same way. So even if we're executing remotely, we still have all of those features available. Last up, since it's new and shiny, we'll load this up under the debugger. I'll enable JIT'd code debugging, and I'll put a breakpoint on that runtime run program function. We'll start that listening, jump back over here, launch the program one more time, and you can see now we're debugging code in the ORC runtime. So I can step through this. We can see the DL open of the JIT'd dilib. We check that that succeeds. We DL sim the main function, check that that succeeds. And then I can step into the main function, and there I am in the Swift code, creating the value printer object. We can step into the get value function, and we can step into print value and see that value get printed. So just to tie this up, what's next for ORC? We've got to refactor the library to improve the layering. So that's going to be the next big upcoming project, is improving ORC layering so that we don't depend on as much of LLVM as we currently do. The new library layering is probably going to look something like this. We'll have a shared ORC shared utility library. JITLink will depend on that. ORC core will depend on JITLink, and we'll break out the parts of ORC that depend on LLVM IR into a separate library. We're going to move ORC out of execution session, but we'll leave the parts of ORC that depend on execution session this should have been execution engine. Leave the parts that depend on execution engine in that library. We need more JITLink backends and COF support. So again, if anybody's interested in volunteering, please let me know. And then hopefully we can get you some updated tutorials and documentation. That's the end of my talk. But yeah, if you're interested, please get involved. Okay, thank you very much.
Thank you, Lang, for this deep dive in the new LLVM JIT infrastructure. Especially the demo was amazing. And welcome to our Q&A session. Please feel free to ask a question in the web interface. We do have 2 questions already. So the first question is asked by Min. He says, I really like the flexibility of the JITLink pipeline. Is it possible to share it or part of it with, let's say, LLD?
That's a really interesting one. We had considered that in the early days of LLD, whether we would try to make LLD and the JIT share code, and we didn't do it at the time. I think at the moment, it makes sense to let them continue to evolve independently. often when you try to share code and linkers, you discover that unless the designs are very similar, all you can share is the relocation expressions, and that's not particularly interesting. But I think once these APIs have had a chance to settle down and we've got more experience with it, there might be an opportunity to revise that. And yeah, maybe we can actually start working towards shared infrastructure between JITLink and LLD.
Thank you. The next question by Jakub. The LLVM-based JITs have reputation of having slow compilation times. Does ORC provide utilities or abstractions that help with keeping compilation times under control, hiding compilation latency, etc.?
Yes. I think there are two parts to this. You can use LLVM in ORC, but you don't have to. That materialization API, materialization concept, as I said, is very, very simple. So if you want, you can tie your own splatting compiler directly into this infrastructure and have your splat compiler called back as needed. The only fundamental overhead in ORC is that dependence tracking. The other thing that you can do, of course, is concurrent compilation gives you the opportunity to hide latency. So if you have long-running compiles, but you can anticipate what code you might need later, then you can start that compiling on background threads. And the ORC safety guarantee means that if you guess wrong about what you need to compile and you have a request come in for code while it's still compiling, all you'll do is have a little bit of extra latency before you actually get the code you want. So yeah, concurrent compilation is great for hiding latency.
Okay. Thank you. Let me mark that as answered. We don't have more questions, but I do have a question on my own. So you mentioned a few times about COF and Windows. So what is the horizon there? What is your expectation?
So I missed a part of that. What was the...
What is the expectation for the Windows support? When is it going to happen?
It's not directly on my roadmap, and part of the problem is I don't have a Windows box to test with. We have COF support in Runtime DYLD, and I didn't say this during the talk, but Runtime DYLD is still supported. Unfortunately, you don't get a lot of the nice new features if you use Runtime DYLD. So we don't have DL open integration, we don't have native thread local variables. But Runtime DYLD will hang around, and because it already has a COF implementation, all it would take is somebody who's motivated enough really to read through that implementation and figure out how to port it to JITLink. I think it's the kind of thing that you could do if you are familiar with the formats. You could probably do this in the space of a few days, maybe a week or so. If you're new to object formats, then I think it would take a little bit longer, but it's definitely doable. And you've got the reference implementation there. And I'm also very, very happy to help out. So again, I want to emphasize, if this is a project anyone wants to take on, please just reach out to me and I'll help you get started.
Okay, thank you. We have one more question that came. Christian is asking, he wants to say thanks for the interesting talk. And what are the implications in terms of security of all these wonderful dynamic features? Are you aware of any CVE related to these technologies?
I'm not, but I haven't been looking at them. This is a low-level API, and there's lots of bare metal stuff going on. So there's plenty of sharp edges for security that you can hurt yourself with. On the other hand, ORC opens up some opportunities to make JIT'd code safer, I think. So that ability to execute JIT'd code out of process is a really big one, because now you can sandbox JIT'd code. So in the extreme, you can have a process that's generating JIT'd code that's allowed to produce new executable memory. And then you can have the JIT'd code running in a process that isn't allowed to produce new executable memory, where read-only text pages just turn up. So that's great. That cuts out a whole bunch of attack surface if the JIT'd code can't create or modify any text memory at any point. Yeah, so mixed bag. Plenty of opportunities to cut yourself, plenty of opportunities to protect yourself if you want. Okay,
thank you. We don't have more questions. I have one more. So could you elaborate a little bit on the reoptimization techniques where you could, you said in your previous slides that you could visit the link graph and then possibly substitute call sites. So
yeah.
How is the reoptimization of code? Is it possible, and is it easy to implement?
Yeah, it's definitely possible. And then there's a broad space of approaches to reoptimization. Some of them are easier than others. If you're happy to leave unoptimized code sitting around, I think one really easy approach to this would just be to say, okay, when we write in our initial unoptimized version, we'll run something like what we saw on that slide. We'll indirect everything so that we could redirect it later. And then maybe on top of just redirecting via stubs, we could add a program counter or just a counter increment to the start of each function. And we could say, okay, we'll check the counters periodically. And if we see a counter for a function get high enough, then we'll go and compile an optimized version of it. And once the optimized version is ready, we'll go and poke the stub function and direct all future calls to the optimized version. That's a simple scheme. And then you can start coming up with fancier and fancier ones. In particular, I like that you might have clusters of functions that you decide that you want to optimize together eventually. And so it would be disappointing if all of your reoptimization required you to constantly be going via indirect calls. But if you can get writable executable memory and you can go back and patch call sites, then as you generate more and more optimized code, you can go back and rewrite calls to become direct in hot regions. So yeah, lots of opportunities to approach that problem. And it's also, that's another one of those big untackled problems. These APIs enable that, but nobody's really dug into it and tried to build in-tree utilities to do this yet. And that would be a fun project.
Okay, thank you. We are towards the end of our time limit, and we don't have a lot of questions. We don't have any more questions. I would like to thank you again for diving and exploring the JIT space and educating our audience. And I would like to thank the audience. So thank you very much, everybody, and feel free to reach out with via the usual channels.
All right. Thanks very much, Vasil. Thanks, everybody, for coming along.